my name is Eric Müller. I work with the BrainScales team. I'm leading software development there since quite some time. And I will show our latest software top level for the BrainScales neuromorphic hardware system. I don't have any reminder on the BrainScales hardware system, so maybe just a sentence about it. We have several generations. The latest generation of the system is it's a mixed signal system. We have analog neurons and synapses on it, around 130,000 synapses on one chip. It's accelerated, so we typically have neuron time constants in the range of microseconds, and it also has one particular feature, which is programmable plasticity. So we have observables on the systems that we can use for plasticity updates or for any kind of computation on the system in a programmable way. So there are some small processors on it, while the majority of the chip is still analog. So the neurons and synapses, as I said, are analog. And I'm talking here about jaxsnn, which is an event-driven gradient estimation framework for analog neuromorphic hardware, but it also aims to be more than that. It aims to be more of a general top-level modeling API for our hardware. As we learned today and yesterday, software is important for neuromorphic hardware to be useful for others. And there are also aspects that current machine learning inspired APIs don't fully grasp. And one of these points is that basically spiking neural networks operate on timed events. So there's typically sparse event-driven communication in these systems. And neuromorphic hardware also often provides high time resolution. So in the case of the BrainScales 2 system, this typically means that we have time resolution in the order of if you think in biological terms, in the order of microseconds, which is 3 orders of magnitude compared to the typical time constant that we have on the neurons. In contrast, the weight resolution that we have in the system is much coarser. Yeah, so it's beneficial to be able to use the high time resolution. The data flow in spiking neural networks can be nicely modeled by signal graphs. So on the top left, you can see 2 populations that communicate with each other. And if you think of spike trains, the typical observables in these systems, they typically have something like a neuron ID, some kind of label, and they happen at some point in time. If you now look at all these machine learning inspired SNN training toolkits, they usually sit on top of artificial neural network training tools like PyTorch. And there, typically, you use a time step-wise formulation of the dynamics. So you formulate your dynamics in terms of Euler steps, and you represent time as a dimension in your tensor, in your data set. And this leads to fixed resolution binning of this information. And obviously, bottom left picture, you can see that this basically removes information from the data that you actually have in the system. Because of that, and there are also reasons for why machine learning toolkits are nice. So for example, the Autograd functionality. And typical toolkits like PyTorch rely on the tensor data structures to implement this Autograd functionality. Because of that, we want to basically look at what can we do about it. Yeah, so how can we get to high time resolution, to event-based mechanics or event-based numerics in the system, while still getting the benefits from machine learning frameworks. So the goals here are explicit handling of time and flexible data structures. We want event-driven numerical simulation to be possible, not required. So we still want to be able to do stuff like we did in the past with PyTorch, but we also want to be event-driven if we want to. And we want to have support for gradient estimation and all this Autograd functionality. On top of that, we also want to have the possibility to optimize it for training purposes on GPUs, for example. So there's this nice XLA, the accelerated linear algebra language. So just-in-time compiling should be supported. Vectorization is a nice thing to have because sometimes you want to formulate your numerics on a scalar on one neuron. So basically, you just want to state the dynamics on one neuron, but you still want to be able to have efficient numerical implementations for full layers. So if you have thousands of neurons, it should happen in a vectorized fashion. So because of that, you want to have the possibility to create vectorized versions of your functions in a programmable way, programmatic way. Creating functions that evaluate the gradient or the vector Jacobian product of a function is also something that we want to have. Other features for us, specifically for BrainScales 2, we want to be able to plug in the BrainScales 2 system, obviously, to use it in the forward path. But we still also want to be able to implement, for example, hardware simulations to incorporate hardware effects without actually using the hardware. Other features like offloading and code generation for these embedded processors would be also nice to have. We didn't do it, but in principle, it would be nice to have. And we want to have, in the end, support for everything the BrainScales 2 hardware supports. So like adaptive exponential integrated fire neurons, multi-compartment neurons, programmable plasticity. So the idea is to have something that can replace our other top levels, which are currently Pine BrainScales and HX Torch. And because of all that, this is actually something that will be also useful for these non-backprop please use cases. Yeah. So if you don't care about the backwards path, it should be still useful. And the outcome of this was basically the jaxsnn library. It's already on GitHub. It allows numerical simulation. It's built on top of JAX. I will skip some of the code examples here. Ask me later if you want to know something about it. And we validated our implementation on an existing data set where we had lots of benchmarks from the past to compare to. And we used the yin-yang data set. There's a representation of the input data. So we have 3 classes to classify. We used event prop training to use an event-based training methodology. We also used other training methodologies, but the main focus was on event prop because we didn't do an event-based implementation of it yet in the past. We made it initially available for the Capocaccia workshop last year, and the software is integrated into the eBrain software distribution. So that's the logo bottom right. So eBrain software distribution is a nice thing. eBrains is an EU project for research infrastructure, and there's a software distribution inside that tries to collect a lot of software packages and client libraries for different hardware systems, also for multi-site HPC simulation, stuff like this. What happens inside our library is basically this. So we have basically a hybrid system. So we have continuous dynamics, transition events, basically spikes. And what you have an initial state that you feed into the system. You have something like an event finder that either finds an event or there's some kind of new input spike to handle. Then we basically perform a dynamics update. We arrive at a point before the transition event. So basically at the time of the event, before the transition, we perform the transition, which would be, for example, in the leaky integrated fire case, would be a reset of the membrane potential. And we arrive at the state afterwards. And that's not time step based, but actually event based now. If we now put in the BrainScales 2 system into this loop, it looks like this. So we have input, we have parameters for the system. We let the system run. We get spikes as output. For the event prop rule, we need additional data, which we can't record on the BrainScales 2 system. So there's an extra box here that calculates the data. That's the current, the synaptic current at the time of the spike. We could measure it in principle, but it's not efficiently possible on the BrainScales 2 hardware. So that's why we calculated. We have some loss function. We have the eProp update algorithm, and we arrive at a weight update. And that's basically what we used to validate it. A result table with a lot of old measurements using other methods. So, for example, an analytical solution by Julian Gölz, Fast and Deep it's called. We compared to time-graded event prop implementations, and we also compared to implementations in one of the existing SNN training libraries that sit on top of PyTorch, Norse in this particular case, and we also re-implemented Norse and JAX. We didn't do fine-tuning to the very end, so this is just to show that in principle we arrive at the right points and it works. Conclusion. So we have an initial implementation of a modular and composable event-driven numerical SNN simulation tool that supports gradient estimation. It's validated against existing baseline experiments, and we have support for offloading this event finding process in the forward pass in actually 2 implementations. We can offload to the BrainScales hardware, and we can offload to a hardware simulation that emulates some of or tries to incorporate some of the properties of the hardware, like noise and quantization of the weights and stuff like that. And currently, the proof of concept implementation is based on leaky integrate and fire current-based exponential synapse dynamics. So it doesn't yet incorporate the adaptive exponential integrate and fire dynamics that the BrainScales 2 system has. Also, there's no multi-compartment dynamics, support for multi-compartment neurons, but that's basically what we have now. So the outlook is basically to implement all of this. And on top of it, we also want to implement online plasticity to be able to combine an outer loop that is trained in a machine learning inspired fashion and some inner during runtime plasticity that happens on the hardware. We want to be able to express it in this framework. And we also want to support basically all the other parameters the hardware exposes and maybe also delays. Yes. We did also a comparison against our existing machine learning library, HXTorch. It looks very roughly similar in terms of performance, but what we didn't do until now is all the scaling measurements. So really large networks, deeper networks, how sparsity in the data affects the performance of the training process, and also the amount of observables that we look at. Also, memory consumption is obviously something that we want to look at, because these traditional PyTorch approaches, if you use tensors, usually you have a lot of overhead in the memory data structures because you introduce time as a dimension. You could do sparse tensors, but there are other problems when using this. I have to mention that this is mostly work by Moritz. He was a student at our place. He didn't continue and he went to industry, unfortunately. And there's also Elias, who is working on our main machine learning interfaces. And Philip is our C++ guy for all the layers that are sitting below. Christian Pehle is co-supervised this work together with me. And he contributed a lot of his knowledge on event-based training. Thank you.